Hey y'all, back for another round of physics. And today we're just going to spend some time working some problems with forces. So the past couple of videos, so 2 videos ago, we talked about Newton's laws. And mainly we're going to be focusing on his second law today. That's the one that's going to be probably the most useful for various problem solving techniques. And then, so that was 2 videos ago. And then last video, we talked about 4 types of nice forces, namely the normal force, the frictional force, weight, or the force of gravity. So I'll put force of gravity. And the last one, normal force, tension. Excuse me, I forgot about that. So if you don't remember those, go ahead, pause now, go back and actually look at those videos and get some just conceptualization of what's going on. So for this video, I figured what we're going to really do is we're just going to sit down and we're going to just go ahead and work out problems. And one of the processes that I tend to follow, I should give that to you first when dealing with the force problem. So of course you already know from the kinematic stuff, you should read the problem, you should reread the problem. And then the next couple of items all kind of go together, but things like drawing a diagram or drawing out your axes. So you have some of those. You should be doing the same thing with these force problems. Okay, so that doesn't change. The slight modification I would make is that with force problems, you should also sit down and identify a system and surroundings. And remember, in one of the past videos, I had discussed how important this is to identify what objects are interacting with the objects you're interested in. So the objects that are doing the interacting are the surroundings, and the objects you're interested in are the system. So it helps to actually define those two. Helps to actually define those two so that you know what forces you should be actually looking at. So that's one of them. The other thing, aside from drawing a physical diagram of the situation, you should also do what's called a free body diagram. Free body diagram. Okay. And what the free body diagram consists of is generally representing your system as a point located at the center of mass, so the center of the object, if you will. We can talk about center of mass later, but say a point at the center of the object, and then you simply draw in all of the forces that are acting on the object. Okay. So we'll have a couple of ideas, or I'll draw a couple of these so that we can get used to them. But most of the time I'll abbreviate this as free body diagram. And again, it's a way of summarizing all of the forces acting on the system in a pictorial manner. Okay. Outside of that, everything else still holds. So let's get at it. So we'll start off with some basic example problems. I think we'll do an example problem of each of the 4 various forces that we talked about, just straightforward, just so that we get some ideas about how to actually approach these problems. And then probably the next video and also in lecture, what we're going to do is we're going to start combining multiple forces together. And I would argue if you understand how to approach these problems from a procedural point of view, then adding additional forces just means that you have an additional term in your equation. Okay, so it might make the equation look longer, it might make the algebra a little bit more arduous to get through, but in terms of how you approach the problem or doing the physics, nothing really changes. Okay. So without further ado, let's go ahead and do a problem with the normal force. And here's what I'm actually going to do. Let's say we have a surface, say a table. So let's go ahead and draw just a quick table here. Doesn't have to be anything fancy. So I'll draw a table there. Boom. Pretty table. And on top of that table, let's say that we have a box. So we'll give the box a mass. We'll say, well, let's color it in. Let's make, we might as well make it a little bit pretty here. Let's color that in. We'll color in the table as well, just for sake of prettiness. Okay, there we go. And we'll say that the box has a mass of m. So pretend we know what what I want to say here is we know what the mass of the box is. It's just that we haven't specified it with a number. So you know what m is. And the question is this: what is the normal force? The normal force acting on the box. Question mark. Okay. So what we're after, we have a box sitting on a table, and we're interested in identifying what is the normal force acting on the box. Okay. So the first thing that I will say is, let's go ahead and let's identify what is our system. What is the object we're interested, object or objects that we're interested in considering. And then after we identify that, let's go ahead and identify the surroundings. In other words, the objects that interact significantly with my system. So go ahead, pause the video, take a second, figure that out, or at least give it a go. And we're back. So let's go ahead and do this. So sometimes it's going to be fairly straightforward, or maybe the problem actually identifies what you're supposed to be considering. Sometimes the problem won't. So in this case, I would say, okay, well, the problem has said the box. They've actually specified what object that we're really, really interested in. And so that's a good indication that we should do something like the box. So then the next thing that we sit down and ask ourselves are, what objects are significantly interacting with the box, or what objects exert a force on the box? And one of them is, okay, well, an object's exerting a normal force. What object is that? And keep in mind, what's our model, our conceptualization of the normal force, that kind of trampoline kind of model. So what's exerting the normal force has to be touching the box. So that tells us right away that we should probably put the table here in the surroundings. Table. But wait, there's more, right? The normal force is what we call a contact force. It requires the two objects to physically touch, right? But there's other forces that don't require the objects to be physically touching. And one of those you also talked about in the last video. Gravity. Right? So the question is, wow. So the other question is, what object interacts significantly? Let's try that again. What object interacts significantly with the box that exerts a gravitational force? And that's the Earth. So we'll go ahead and put Earth down here. Welcome to Earth.
Ah! That's right! That's right! Get up! Get up! That's what you get! Look at you! Ship all banged up! Who's the man? Huh? Who's the man? Wait till I get another plane! I'm lining all your friends up right beside you! Where you at, huh? Huh? Where you at? Ah! Welcome to Earth.
So now we have our system and our surroundings. And this is, again, as you get more familiar with doing these problems, as you advance into other classes, you might not actually put this down on paper. But I want you to be doing it right now just as a good exercise in practicing. Okay. So we have our system, we have our surroundings. Let's go ahead and now think about Newton's 3 laws. And namely, I'm going to focus on the second one. That's generally where these force problems are going to be starting. So let's go ahead. I'm going to clear this space. What I'll do is I'll move this down here so we still have it visible, but it'll just give me a nice palette to work with over here. So what we're going to start off with is we're going to, oh, excuse me, I jumped the gun. We need a free body diagram. So how we're going to do this, we've identified our system, it's the box. And rather than drawing it as an object with, physical dimensions and extent, we are going to represent it as a dot, a point, and you can conceptualize this point as being the center of the box. Okay? Physicists are not artists. The whole point of a free body diagram is to eliminate anything that's just not helping us do the problem. Okay. So then we will ask ourselves, we have two objects in our surroundings, the table and the earth. Let's go ahead and focus on the table. What force is the table exerting on the box? See, I got this. We already talked about this is the normal force. Good. Second question. In which direction is that normal force? And I'm hazarding to say you said up, right? Now, up's not good enough for us, right? Because say you're in outer space. There's no up in outer space. So one of the things that we should accompany either the physical picture or the free body diagram is that we should draw in our axes. So I will go ahead and I will call this direction the y direction, and I'll call this direction the x direction. So just putting some axes in. Now I could say, according to the axes that I've drawn, what direction is the normal force? You say the y direction. I agree. So now we can draw an arrow representing the normal force on our free body diagram, and we label it. Okay. The only thing that gets drawn on free body diagrams, the object as a point, the forces as vectors, and maybe you can include an axis off to the side. Those are the only things that I should see on a free body diagram. Now the next question, what direction? We've taken care of the table. How about the earth? You say, I got this. That's the gravitational force, and that's downwards. Or, because we're careful about up and down, it's in the negative y direction. So positive y is up. I will put the force of gravity or the weight going down. Second question, how should the length of the arrow representing the force of gravity acting on the box compare to the length of the normal force, which I have already drawn? Hopefully you know they should be the same. So I should take the length of this arrow and I should replicate it for the gravitational force. Oops. Something like this. There we go. And we'll call this F of G. Now, how did I know that? We'll use this idea for the next piece. On your free body diagram, you should try to scale those. If you have an idea about the magnitudes of these, you should try to scale them appropriately. So I have no idea what the value of the normal force is right now, but I do know that the gravitational force should be equal to the normal force, but in opposite direction. So now that we have our free body diagram completed, we can go ahead and start off with Newton's second law. So I will go ahead and write down Newton's second law. Okay. And remember, this is a relationship equation. Now, I've got vectors in here. You see, so this is actually three equations, the x component, the y component, the z component. And the question next is, which component am I actually interested in to do this problem? There's the y component. You see that all of my forces are in the y direction. I don't need to worry about the x components and the y components. I can the x components or the z components. I can forget about those. It's zeros everywhere. So the next step is, okay, I will say for simplification, I am going to consider the net force in only the y direction. Now I'm subscripting this with a y. You could put, off to the side, you could just say y direction. That's okay. You need to indicate somehow that you're only considering one of the three directions. And this is just, again, establishing good habits. Later on, it will be that we maybe ignore the z direction, but you have to use both the x and the y. Okay? So you have to practice good habits, get them established early. Now the next idea, we'll focus on first the acceleration. What's the acceleration of this box as it rests on the table? 0. And again, look, it's in the y direction, right? The box isn't jumping off the table, or it's not falling through the table. It's 0. So I end up on this side, I can just write 0. Say I'll put over here on the side AY equals 0. Box at rest. Okay. Or not accelerating. Okay. Now on this side, we have to remember, what does the word net mean? It means all of the forces acting in the y direction. And this is where, nose itch this morning. This is where the free body diagram really helps us out. It allows us to visualize all of the forces that are acting on the object. So if you've done your free body diagram correctly, then it's not hard to know what the net force is. So we go through. The normal force, that's pointing in the positive y direction. So I'll just write the normal force, N. Then I have the gravitational force in the negative y direction. And please be careful. Here you have to pay attention. Negative y. So I'll so I'm adding them together. We're using the idea of superposition, but this gravitational force is in the negative y direction. Please also note I've dropped my vector signs on these two forces because I previously specified that I'm dealing with the y direction, and these forces are only in the y direction. Okay. The penalty for dropping the vector signs, for specifying the y direction, is that we have to explicitly write in our negative signs. That's why this negative sign comes in. Again, I emphasize negative y direction. So the next step we are left with, and we're almost done here, let's go through and substitute in the definitions that we have for each of these forces. So we look at the normal force and we say, we don't have a specified definition. That is very situationally dependent. So we don't know that. And in fact, we're asked to find that. Okay? So we'll leave this as N. But for the gravitational force, we definitely have an expression for that, a definition. That's also known as the weight, and that is given by the mass of the object times g. Presumably, we're doing this on the Earth. So it equals 0. And you probably already used this idea when drawing your vectors in the first place. Let's move the mg to the other side, and we're done. We have that the normal force in this situation is equal to the mass of the box times the acceleration due to gravity. And I'll go ahead and square that off so that we know that that's our final answer. We're done. Now, one of the things that I will warn you about is that it is common to look at this situation with the table and the box and say, oh, the normal force is the same magnitude as a gravitational force, but in opposite directions. This is because of Newton's third law. So you have two forces equal in magnitude, opposite in direction. This is a third law pair. And now pause the video for a second, ask yourself, why is Greg emphasizing this? And is this actually a Newton's third law pair? Hopefully you see, no, this is not a Newton's third law pair. You say, what do you mean, Greg? They're same magnitude, opposite directions. That's what Newton's law says, Newton's third law. And I say, you're missing a very important point that I emphasized in the video, that past video. I said, Newton's third law pair is between two objects. Two objects. Let's go through and look at this. How many objects are we dealing with this pair of forces? Well, the normal force is the box and table. Okay, that's the normal force. Over here, and now you see it already, this is the box and earth. Right? Not the same pair of objects. Newton's third law requires two objects. And you're looking at the forces between two objects. Here you're looking at the force of three objects, right? The box, the table, and the box and the earth. So this is not a third law pair. Okay? Even though they are in same magnitude, opposite directions, that is not a third law pair. Okay? Convince yourself that's the case. Okay? Good. So that's the normal force. We'll go ahead and get rid of this. Okay, perfect. So that's taking care of the box sitting on the table. Why don't we move on to the tension force? So tension force. Okay. And to give you some sort of idea, let's say we're interested in the tension force in a rope. So we'll make a string on the end of which a box hangs. So we'll make a box and set it as mass m again. Okay? And why don't we get an idea about what the tension force is? So what is the tension? Sometimes instead of tension force, it might just be tension in rope. Okay? So sometimes you'll see tension force, sometimes you'll just see tension. Okay? So starting off like we did the last time, why don't you take a moment and identify what's the system, what's a good choice of system, and what's a good choice of surrounding. Okay, got it? So a good choice, I would argue that probably the best choice in system is, again, just choosing the box. So I'll put box here. And in our surroundings, we have two objects which significantly interact with our box. One of them is through this contact force. Again, tension is a contact force. So the box is touching the rope. There's a force that's being exerted because of that connection. And so I'll put rope. Okay, that's one thing. And the second one is a non-contact force, one that there's a force exerted between the box and presumably, again, the earth. That would be the gravitational force. Okay. So we've got our system and our surroundings. Let's go ahead and why don't we draw next the free body diagram. So go ahead, pause the video, draw a free body diagram for this situation. Okay. And being the artist that I am, I'll go ahead and draw. There we go. There's our box. And you can consider this point again to be the point at the center of the box. So this represents my box. And I have two forces acting on it. I have the gravitational force. I think I used blue last time, so we'll keep with that color scheme. We have the gravitational force pointing downwards. I'll go ahead and label that again FG. And we have the normal force. Oh, excuse me, I've gotten all confused. We have the tension force that's pulling upwards on the box. There we go. And I'll use T to represent that tension force. Good. So now, oops, one last thing. You say, wait, Greg, there's one thing you told me about that I should include. Set of axes. I'll go ahead, and this time I'll draw it on my free body diagram. I'll call Y positive again, and I'll call X to the right. Okay. I'll just make my life easier. Yeah. So now let's go ahead and let's start using this free body diagram. We've got our system and our surroundings, our free body diagram. Let's go ahead now and start working away at Newton's second law. So we have F net equals our mass times our acceleration, or I should say is related to the mass of the system times the acceleration of the system. And in this case, I'm again working in just the y direction. So I will have F net in the y direction is equal to the mass of the system times the acceleration in the y direction. Okay. And you say, why do I write this twice? Again, this is three equations. This is one equation. By doing it this way, by writing it twice, you are showing me that you recognize that this is a three equation relationship. This is only a single equation. Okay, so there is some value here that's being introduced, some knowledge that you're conveying to me. So let's go ahead. If we ask ourselves, well, if the box is hanging here, what's the acceleration in the y direction? You've got this. You said this is just 0, so I'll put 0 in there. Okay. Over here, the net force, we can look at our free body diagram. We say, well, the tension is going upward, so since I called up positive, I'll leave a positive sign in front of the tension force. Since I called down negative, I will put a minus sign in front of the gravitational force, Fg. Now I'll go ahead, I'll substitute in values. So I've got my tension, minus mg is equal to 0. And so if I want to find the tension as prescribed in the problem, I'll move this mg to the other side, and I end up with tension is equal to the mass of the box times the acceleration due to gravity. And there is our final answer. Now, one of the things I should point out, one of the things that's a common theme in physics is stripping away all of the surface features, all of the specifics about the problem, and identifying the physically relevant quantities or the physically relevant ideas that the problem is presenting. Okay. So here, what I want to point out to you is, if you notice, we have a physical situation that's different. So instead of a box sitting on a table, I have a box hanging by a rope. So physically speaking, they're different situations. Okay. But then afterwards, once I get down to this free body diagram right here, if you notice, the free body diagram for the past problem, the box sitting on a table, looks exactly like the free body diagram here for the box hanging by a rope. The only thing that's different is that in the previous problem, we had the normal force going upwards. In this problem, we have the tension force going upwards. Well, that's just a variable, right? That's just some force. You could have called the tension force N if you really wanted to. From this point onwards, from the free body diagram point onwards, for the rest of the problem, the two problems, the box sitting on the table and the box hanging on the rope are exactly the same in terms of your approach. In fact, the free body diagram's the same, and our process of going through and finding the answer is exactly the same. And the answer was the same, right? The last time we had the normal force is equal to the gravitational force acting on the box. Okay? And so that's one of the cool things about physics is if once you strip away some of those surface features, the underlying ideas, the underlying approach to the problem stays the same. And I would encourage you to focus on that, to keep reminding yourself about this as you're going through. Of course, I want you to get more proficient about dealing with the equations, but I also want you to take a minute every once in a while, step back and remind yourself, or at least look at it and say, wait a minute, I've done this problem before. It looks different, but I've done it. I've done this problem. Okay. So that's all I have for that one. So let's go at another problem here. And this one we're going to deal with the friction force. So frictional force. Friction. And I'll go ahead and set up the problem here. What I'm interested in, let's say you start with a box of mass m and let's say initial velocity in v naught slides across floor. If I guess we'll need a coefficient here. Let's say if mu k is equal to 0.25, how far does box slide? Question mark. And in fact, now that in retrospect, I'm making this up a little bit off the top of my head. Let's just say that you know the coefficient of kinetic friction. Let's say that it's, you know, you have mu k, but we're going to leave it as an unspecified value. So you know the mass, you know the initial velocity, you know mu k. Okay? And what we'll do is we will find a distance as a function of those three variables. Okay? Clear on what we're doing here? Sorry. Coffee. Need coffee. Okay, let's rock and roll. So one of the first things that we should do is we should take this word problem and we should turn it into a diagram. So let's get a floor. Here we go. And let's get a box. Boom. One box made to order. So it's a mass m. It's sliding along at some speed of v naught, okay, or some velocity. Okay. And one of the things that we should look at, so the past two force problems, we haven't thought about how many steps are needed. And in fact, I apologize. Essentially, it's a one-step problem. We apply Newton's second law, boom, we get our answer, and we keep going. Here, we should pause and we should ask ourselves, how many steps do we actually need for this situation? Okay, so I'll say pause, think about it. And hopefully you see that we're actually going to use 2 steps for this situation. And let me plan this out for you. So the first step is we need to find the acceleration of the box. Okay. So once we have the acceleration of the box, how does that help us with finding the distances? And hopefully you see that the acceleration of the box is going to be constant. A is going to be constant, and therefore we should be able to use the kinematic equations. To actually find our final distance. Okay. So this is a skill that you need to start developing. So you say, okay, how many skills do I have? Well, first of all, identifying initial and final states. That's a skill that needs developed. identifying how many steps a problem requires in order to solve. Second idea, identifying systems and surroundings. Okay, that's another skill that you need to be able to develop. Okay, so I know this is a lot coming at you, but that's partially how it is. Okay, so again, practice, practice, practice. So in this case, we actually need 2 steps. So that's also why I've said, okay, well, we've done a couple of simple problems. Let's ramp it up just a little bit. Okay. So let's go about this. So for step 1, finding the acceleration of the box, what physical idea are we going to use to do that? I got this. What we're going to do is use Newton's second law. So before we apply Newton's second law, we better do a free body diagram. Oh, excuse me. I'm skipping steps here. We should identify our system and our surroundings. So go ahead, take a minute. Hopefully you got it. System is still the box. That would probably be the best choice of the system here. And the surroundings, we have to be careful. And you might actually say, okay, well, how many things in the surroundings? We actually have 3 things we need to worry about here. So the first one is the floor. And I'll put in parentheses here. This accounts for both a normal force, right, and the frictional force. So there's actually 2 things that the floor does. And then we have the force of gravity, so that is due to the Earth. We've got 2 items, but 3 forces. Now we do our free body diagram. So take a moment, pause, draw your free body diagram. Okay, I'm good to go. Hopefully you are. Here's my center of my box, and I will draw my 3 forces. The first one is, of course, we have a normal force going upwards. So I'll label that as N, my normal force. We have a gravitational force going downwards. Oops. Remember to hit the shift key first. Gravitational force going downwards. There's F of G. And what's the third force? What third force do we have? And which direction is it? We have the frictional force. Now that one's a little bit tougher to figure out, but because the box is sliding to the right, the frictional force is going to be to the left. You know that as the box slides, it must slow down. That means that there's a force acting on it in the opposite direction. So the frictional force will be going this way, to the left. FFR. Okay. And there we go. Of course, we're missing one more thing. Let's throw that in there. And just for kicks, why don't I say, I'll call the going to the left positive. So let's call this direction, we'll call that positive X. And for kicks, why don't we call down positive Y? Okay. This is, I'm doing this partially just to show you that this choice doesn't matter. We should still be able to solve the problem. Okay. So let's go ahead and get rid of this piece. Well, you've got that in your notes. Okay. So now let's go ahead and we're going to apply Newton's second law. F net is equal to the mass of the system times the acceleration of the system. Of course, here we should ask ourselves, the acceleration, which helps us determine how far the box slides, is it the acceleration in the x direction or the y direction? And here, it's the acceleration in the x direction. So this situation, I am going to look at the x direction. X direction. I'm going to start with that. And so I have F net in the x direction is equal to mass times the acceleration in the x direction. Cool. Well, now let's go to our free body diagram, and we see that the frictional force is pointing in the positive x direction. Cool. So let's go ahead and we'll put that in. Force of friction, Fr. And that's the only force. You see, that's the only force that's in the horizontal direction. So we write this as MAX. Okay. Now let's substitute in the definition of the frictional force. And that definition is the normal force times mu k. The coefficient of kinetic friction is equal to MAX. And now the question is, can I get an expression for the normal force? I need, because the frictional force depends on the magnitude of the normal force, I now need to figure out a way to get that value. And do you see what we're going to do? Which direction is the normal force in? It's in the y direction. So let's take another, so here's where we're actually going to take this Newton's second law, and we're actually going to form two equations out of it. We have the x direction, but we also have the y direction. So I write F net in the y direction is equal to MAY. And now let's take a look at our free body diagram. Our gravitational force is in the positive y direction based on my choice of axes. So I'll write FG. And my normal force is in the negative y direction. So I'll put minus n. And what's the acceleration of the box in the vertical direction? 0. Doesn't jump off the surface. It's not falling through the surface. So we write 0 here. Okay. And so I will plug in the definition of the gravitational force, mg. I will move the normal force over to the other side. And now I have an expression that gives me the normal force in terms of the variables that I am given, namely the mass. So now I can take this expression and I am going to substitute it in over here. So I get something that says mg, that's me substituting in the expression for the normal force, mu k is equal to ma in the x direction. You say, I got this. Look at that. Oh, goody, goody. Goody, goody, goody. The m cancels the m, and I end up with something that says that my acceleration in the x direction is equal to mu k times g. And I'll go ahead and I'll square that. That's a result that we'll need later. So I'll go ahead and square that. Okay, good so far? You say, but wait, there's more. There's more that we have to deal with here. So I'll put this up here. That's just the first step. We still need to use this to find our final distance. So let's go ahead and get rid of all of this. Presumably you have it on your paper now. And now we're set on the second step. In fact, we don't need this either. So now we're on the second step. Second step is applying the kinematic equations. And I said, hey, when you do the kinematic equations, you should identify an initial state and a final state. So take a moment. What's a good initial state? What's a good final state? You got it? Hopefully you see that a good initial state is, say, when box moving at, I'll say, v naught. Okay? We're told that, right? It's initial state. Final state, this is a little bit more tricky, but how far? That hints at what we want our final state to be. We'll say when box stops. or in parentheses, I'll put v final, the velocity vector is 0. Yeah, good. And I know you probably had that. So we should probably draw a diagram. So if this is my initial state that I have right here, yeah, yeah, this is our initial state. And keeping in mind, excuse me, I erased those and I shouldn't have. Keeping in mind, we called this direction positive x and this direction positive y. So that brings into a note, you are free to choose an orientation of axes. Okay. But once you choose an orientation, you should not change your axes. So this expression that we got for the acceleration, you notice how it's positive. Okay. That's positive with respect to the system of axes that you have chosen. In other words, the acceleration vector points to the left in the positive x direction. So we can't, now that we've made a choice on our axes, we can't change anything. Okay. So we have this. Why don't we go ahead and set the initial origin right where the box is located? So maybe really what I should do is I should take this and let's set it right here. There we go. So I'll offset that just a little bit just so you can see it. Okay. So that's really where I want the origin to be. Okay. So if I write down all my initial quantities, I've got something like, I said, hey, be systematic at this. I'll put in the x direction, I'll put the acceleration in the x direction. Be systematic about this. Since we're starting at the origin, this is 0. We're given a value for the speed. We'll just call that v naught, or the velocity, but since the velocity is only in the x direction, the velocity and the speed are the same in magnitude, I guess I should say. Acceleration, we have this as mu k times g. Just kind of weird. It's kind of weird to have a g, the acceleration due to gravity, in a horizontal, or a component in the horizontal direction. And that's something that friction does. It takes, the normal force, through the normal force, it introduces the g, but it's in the horizontal direction. So that's kind of cool. For the final state, I'll draw the final state, the box over here. We don't know the final distance. We'll call x final. That's a question mark. That's actually what we're called defined. Our speed in the x direction, final, is 0. Good. And the time, no idea. We have no idea how long it takes to get that far. So what we need is the kinematic equation that has final position and does not involve time. I got this. You got it? I'll write it down. We have v final squared, put x direction, minus v initial in the x direction squared is equal to 2 delta x, I'll put ax. And now you see why I keep putting these subscripts in. It's reminding me I'm only dealing with the x direction. Well, let's go ahead. Let's plug and chug. Let's plug in our values. We get 0 here. We have, I'll just leave it as v naught now, equals 2 times x final minus 0. So I'm plugging in just my zeros, and I'll plug in the expression here, mu k times g. Solve for x final. So we need to get some, got to get some rearranging going here. All right? Something bugs me. What's bugging me? Oh, yeah. Okay. Got it. Keep going. Yep. So let's rearrange, and I'll divide. So I have negative v naught squared. See, I had to remind myself of what's bugging me. Divided by 2 mu k g equals x final. And there we go. There is the expression. There is the final distance that the box travels. Now, one of the things that I said, oh wait, something bugs me here, is this negative sign. Why does this negative sign actually makes sense. So this negative sign in the final expression. I'll say, which direction do we call positive? We called positive x to the left. Which direction does the box move? To the right, which means the final position of the box indeed should be negative, right? If my origin's here and the final position's here, you can see that's in the negative x direction, okay? So this does make sense that I have the negative sign. Let's ask some other questions. We're going into sanity checks. Okay? What happens if the box starts off with a higher speed in the x direction? It should go further. That's what this, right? It's in the numerator. Speed is in the numerator, which means if speed goes up, my final distance traveled goes up. How about if the coefficient of kinetic friction goes up? Should the box travel further or less far? Less far. And indeed, you see, because this is in the denominator, if mu k increases, x final goes down. So that at least a couple of these things make sense. The sign makes sense. The fact that it's v naught in the numerator and mu k in the denominator, those make sense. The negative sign, oh, I already mentioned the negative sign. So those are all things that say, okay, I think I've got the right answer here. Okay. So that's just our first foray into two-step problems. And you notice you combined Newton's second law and used two equations from Newton's second law, and you coupled it with a kinematics equation to actually get the final answer. Okay? Get the next problem here in a second. Okay, so another problem here. And this one we're going to be dealing with, again, two forces and just thinking about how to combine them. And I thought we would do this one as a primer for some more difficult ones. And I'll say it's a box on a ramp. Box on ramp. Okay. And so let's get an idea. Why don't we say, what's the acceleration down a ramp? So given a box of mass m on a ramp of angle theta, find the acceleration down ramp. Okay. And just like anything, we should probably start off by drawing a picture. So let's go ahead and let me just draw a ramp here. And we will call this angle theta right here, so the angle of the ramp. And I guess we better put a box on here, so let's go ahead and put a box on the ramp. And go ahead and fill that box in, and lastly call it a mass m. So here's our physical situation that we're after. We've got a box on a ramp, angle theta, and we're interested in finding the acceleration. So let's go ahead, get an idea about what's a good choice of system and what's a good choice of surrounding. Okay, you got it? So here again, I think that probably the best choice of system would be the box, since that's the object that's accelerating and experiencing a bunch of forces. And the surroundings, we've got, again, two objects. We'll start with the ramp, and I'll put in the normal force. That's the force that the ramp exerts on the box. And then we have gravity, so I better put Earth in here. Good. So those are the two ideas that we have here. Now, free body diagram. That's the next step. So we've got our system and our surroundings. So let's represent our box. There we go. And here's something that we have to be more careful with now. If I'm thinking about the normal force, if I want to draw in the direction of the normal force, how does the direction of the normal force compare to the surface of the ramp? You got it? And this is something that now that I'm sitting here doing the problem, I failed to actually note in the last video. So here's the issue, is that the normal force is always exerted perpendicular to the surface. Okay, I'll say that again. The normal force is exerted perpendicular to the surface. So we look at the direction of the surface, and the normal force has to be perpendicular to it. So we better put the normal force something like in this direction. Of course, I'm eyeballing it, but that's roughly the direction of the normal force. So put N here. Perpendicular to the slope or the face of the ramp. Now the gravitational force we luck out on, of course. We just have that going straight down. Fg. Okay. And we have nothing else that we have to worry about. Sweet. Tally ho. Now, if we're following our process that we used last time, now we're going to sit down and we're going to start playing with Newton's second law. So we write our relationship, A. Here we are. And, of course, we should specify some axes choices. Now, here's one that this situation, it works out a lot easier if we do not choose our standard axis orientation. And what I mean by that is pretty much up until this point, we've been choosing our axes like this, or some variation where X represents the horizontal direction, Y represents this vertical direction. In this situation, and again, you don't have to do it this way. You can solve it without doing this. But in this situation where we have a ramp, probably the easiest choice of axes is actually not horizontal and vertical, but it's usually easier if we do parallel to the ramp as being one direction, say X, and perpendicular to the ramp as being the second direction, Y. Now, why is this? Simply put, it's nice to orient our forces or our axes with the direction of one of the forces. Now, in this particular case, I've oriented it so that the y-axis is parallel to the normal force, and that makes it easy. In fact, tomorrow, the next video where we include frictional forces, we'll also have that will introduce a force that's in the direction of x. So every once in a while, it comes into play where this is a better choice, specifically, usually with ramp problems. Okay. So let's go ahead and do this axis. So I have x as being down the ramp. I have y as being perpendicular to the ramp. In fact, let me move. Well, okay, yeah, we'll leave it like that. Okay. So we're interested in finding the acceleration down the ramp, the acceleration in the x direction. That's another reason why it's nice to choose this set of axes. The acceleration will only be in the x direction. So let's go ahead and let's specify that. So we're looking at the x direction, and we can write the net force in the x direction is equal to m times a in the x direction. And now we look and we say, okay, all we have to do is find the net force in the x direction. Looking at it, is the normal force in the x direction based on the axes we've chosen? No, it's not. We chose our axes so that the normal force is in the y direction only. So there's no x component there, therefore we don't have to worry about that. But now if I look at my force of gravity, okay, so my gravitational force, let me redraw that. My gravitational force is straight down, like this, Fg, and my axes are like this. Here's my x direction. Excuse me, let me do that in black. Here's my x direction, something like this. And here's my y direction, something like this. And hopefully you can see that my gravitational force here actually has a component in the x direction and a component in the y direction. right? You can see that it has a component in this direction, it has a component in this direction. So the penalty for putting our axes parallel and perpendicular to the surface of the ramp is that now our gravitational force has two components, a y component, a component that's perpendicular to the ramp, and a component that's parallel to the ramp. So what we need to be able to do is figure out how to actually express this force in terms of the y direction and the x direction. So we have to take a small break and do some geometry. Woohoo! All right. So I'm going to leave this portion up because I want to be able to reference that or continue on. I'm going to go ahead and get rid of this piece. Okay. Oops, excuse me. There we go. So I've gotten rid of that. And if I actually look, I'm going to actually draw another triangle here. Okay, so I'll draw a triangle like this. And if I look, and I mean for this to kind of be this triangle, if I look, we notice that my gravitational force is going to be straight down, right? My gravitational force is like this, Fg. So I'm kind of combining my physical diagram with my vector diagram. So the question really becomes, if I know this angle theta, what would this angle be, knowing that this is a right triangle? I got this. This piece of cake. This angle would be 90 minus theta. So 90 degrees minus theta. Okay. Now the next piece I'm going to do is, okay, let me draw in the perpendicular to the ramp, something like this. So I'll draw that in now. And if I know that this angle right here is a right angle, and I know that this tiny piece is 90 minus theta, then what is this tiny piece going to be? Theta. So I got a theta here. So we're just using a little bit of geometry. The idea that for this triangle, this, I'll outline it in yellow here, for this triangle, which involves the given angle theta, we know that this angle is 90 minus theta, and then looking at this right angle, that makes this small angle here theta. So going back to this diagram that I have, I can say, I got this. This angle right here is theta. So if I have the hypotenuse of the triangle right here, FG. I know that this angle is theta. How do I get this piece that's in the x direction? Got it? Well, this piece right here is opposite the angle, and the trig function that deals with the side length opposite the angle and the hypotenuse, so opposite and hypotenuse, is sine. So the gravitational force in the x direction would be the hypotenuse, f of g, times sine of the angle. That will be equal to m times my acceleration in the x direction. Convince yourself that that makes sense. Okay, convince yourself, because we're going to use this again. This comes up a lot, but we'll use it again in the next video. Okay? So we have Fg sine of theta. Now, of course, let's use our definition of the gravitational force. Mass times the acceleration due to gravity, sine of theta. And this will be equal to, this is related to the acceleration that the box experiences. We say, oh, goody, goody. We can cancel out the masses. And so we end up with an expression that says the acceleration down the ramp in the x direction is equal to the acceleration due to gravity times sine of theta. Cool. So the fact that the mass cancels out means, it doesn't matter. This could be a box. This could be a marble. This could be an elephant. It doesn't matter. You say, wait a minute, that doesn't make sense. That seems wrong. I know if I put an elephant on this ramp, it should accelerate slower than a marble, or say a hockey puck, or, you know, take your pick of objects. Now let's go ahead and sanity check. The other thing that I think of for a sanity check is that if angle theta is 0, so then you have a flat surface, a perfectly horizontal surface. And in that situation, will the box slide? Say, of course not. Of course, if there's no angle on the ramp, the box is just going to sit there. So what happens if we put in theta is equal to 0? We see that we get sine of 0 is 0 and the acceleration is 0. That makes sense. That's what we would expect. If it's a horizontal surface, the box doesn't accelerate. The equation tells us that. You could say, what happens if the surface is perfectly vertical? You would expect that the box would simply fall. In other words, it would accelerate at 9.8 meters per second squared. Remember the square. So if I substitute in theta equals 90, sine of 90 is 1. And I do indeed end up with the acceleration would just be the 9.8 meters per second squared. Okay. So I think that's it for the practice problems, or at least this first round of problems. You've got about 3 or 4 of them, and it's taken a fair amount of time to go through. To say, if there's a question, please bring it to class. If not, the next video we'll do some more complicated problems. Namely, we'll add in, say for example, a box with friction, or maybe we'll actually have a ramp with friction and a pulley. So we're going to start combining several of these ideas, getting more complicated expressions. Thanks for your attention. I'll see you next time.